So hi, my name is Rachael Beaton. I am a Hubble Fellow, Carnegie Princeton Fellow at Princeton University. And I'm also the Apogee 2 Science Working Group Chair. I'm not going to talk about Apogee 2 very much, but if you are thinking about using Apogee 2, I'm happy to talk about that later today. And the byline I like to give when we're starting this talk is from this quote by John Muir, which says, "When we try to pick out anything by itself, we find it hitched to everything else in the universe." And so in a talk about measuring the Hubble constant, we're going to talk about stars, galaxies, cosmology, subsets of galaxies, and chemistry. Everything that you can possibly think about goes into this measurement, except for black holes. And the Hubble constant and the distance scale is something you learn about in Astro 101. And it's typically taught by starting here in the Milky Way and working out until you eventually measure the Hubble constant. So stepping to the Large Magellanic Cloud and beyond. But for this talk, and the way I like to think about the Hubble constant, I want to employ a concept called backward design. It's used commonly in education. So those of you who've been in the professional development program probably know all about this. So here's some direct crosstalk between education, training, and science. But it's also used in engineering. So basically, we're starting with a spec. I want to get to a 1% measure of the Hubble constant. And now we're going to work backwards from there and say, what do I have to do to get there at every stage? So this is going to be a little bit of a different way than you think about it, the Hubble constant. So this is the original Hubble diagram from Hubble 1929. And basically what you're seeing here is distance on the x-axis and recession velocity on the y-axis. And an important thing to note about this figure is that generally we put the easy thing on the x-axis and the hard thing on the y-axis. So in 1929, Hubble thought distances were the easy thing, and recession velocities were the hard thing. And that was true, because to do this, you had to be able to stack spectra of stars for several nights worth of data to measure these velocities. And that was invented at Lowell Observatory, actually, by Slipher. So Hubble makes this plot of distance versus recession velocity, sees that there's a trend, and calls the constant between velocity and distance the Hubble constant, of course. As he called everything after himself. So this is Hubble, of course. I always like to highlight that this is the only picture we have in the Carnegie Archive where he is close to smiling, and it is because of the presence of his cat, Nicholas Copernicus. Okay, so the history of the Hubble constant from Hubble all the way to the Key project, which is where I'll start this part, is a story of not knowing what we don't know, but being pretty confident that it's not there and it's not a problem. So here, Hubble's original measurements. You see a huge change in the Hubble constant when Walter Baade, also a Carnegie astronomer, discovered there were actually two Cepheid populations, one from an intermediate class of stars, one from a young class of stars. All of a sudden, the Hubble constant drops a great deal, and the error bars look reasonable. And then continues to drop as better and better measurements are taking place. Bigger telescopes are coming online, like Palomar, in this era. And then it goes into this furious debate between 50 and 100 from about the 1970s all the way to the HST Key project. A most notable timeline here is when Cook, Aronson, and Illingworth actually were able to detect Cepheids using these newfangled charge-coupled devices. M101 had been the limit of the ability to detect Cepheids on photographic plates. Sandage tried really hard, but could never do it. It started a whole bunch of arguments about the brightest stars in the galaxies and what they mean and all this kind of stuff. But then Mark Aronson pioneered really doing this with charge-coupled devices and measured Cepheids for the first time. And to me, that marks the end of photographic plate as the dominant way to do astronomy. And then moving forward, 50 and 100, bouncing back and forth. What we didn't know during this time is that the universe is actually accelerating. All of a sudden, so one of the reasons why Sandage was really arguing for 50 was to get the age of the oldest star clusters, which we thought at the time was around 15 billion years, to get that to line up with the Hubble constant. If you have an accelerating universe, that falls away pretty easily. Okay, so we don't know what we don't know. And when you're thinking about the Hubble constant, you have to keep that in mind. So here's a modern Hubble diagram. This was in my paper last year. This is not the most up-to-date Hubble diagram because data is coming out all the time, but it's one that I can animate easily and explain. So where we actually measure the Hubble constant these days is out in the Hubble flow. So this is above a redshift where you can actually measure you can say that you have redshift when it's greater than 0.01, all the way out to a redshift about 0.1. And that's where we can make easy measurements from the ground. What you're seeing here are all of the supernovae from two major projects, the Carnegie Supernova Project in the Southern Hemisphere and CFA4 in the Northern Hemisphere. You'll note that the gray points have bigger scatter, and the red points are a little bit tighter. And that's the difference between using supernova in the near infrared and in the optical. You have a much stronger handle on the local extinction and other properties, and that's why this is a tighter relationship. And we measure the Hubble constant out here because we now know that the Doppler motions of galaxies can be dominant inside of this distance. So to get into the Hubble flow, you need to be at a distance around 50 megaparsecs. We can't do distances that far right now. So the scatter in the supernova and the Hubble flow, where we actually measure that slope, is about 0.5%. And that's because of numbers. The scatter here is about 0.15 magnitudes, which is about 7.5% in distance. And when you divide by the numbers, you get down to about 0.5%. If my goal is to get to 1% H naught, this is a quarter of my variance right there, before I've even started to calibrate anything, right? So to calibrate this relationship, from the distance ladder, we have to get very tight on our uncertainties. So the relationship has calibrated, or we set the 0 point using a local sample. So at the time that we made this figure, there were 8 supernova in all of human existence that had independent distances to calibrate the 0 point, okay? 8. In about 3 days, within the time that I posted my paper, Adam Rees posted a paper with 19, okay, in 2016. So then that's what anchors our entire measurement of the Hubble constant. And I'm harping on this because it's a very important point. So this local sample, we don't actually use their redshifts. You can see how big these recessional velocity errors actually are, but it's quite small. And the uncertainty is set here. It anchors in around 1.5 to 2%. So we've sailed past 1% now, if that's our ultimate goal. And it depends on, this is a tricky number to argue, it depends on the number of galaxies and how you're measuring the distances and things like that. So here's the whole Hubble diagram that we showed, the local sample anchoring this relationship, and then we measure the slope out here. And that 2% for the number of calibrators, and that small number used to be okay when there were so many other uncertainties that we had to worry about. So this is the Key project in 2001, and this is the Shoes result in 2016, where they measured about 2.5% distance. So 2% is sort of like where we're aiming. So it's the dominant error term. And it's a little tricky in this, the way that they like to separate their errors is a little tricky. So you have to combine a bunch of these little color terms to actually get the true uncertainty on the 0 point. But trust me, it's in the 2% ballpark. And so that 2% is no longer okay. And the reason is, from the Key project to now, we've seen a discrepancy between the cosmic microwave background, indirect measurements of the H naught, which are coming from the young universe, the Z of 1100 universe, and the distance ladder coming from the Z of 0 universe. So the Key project and advancements therein, which is improvements in technology, improvements in our understanding of Cepheids, wonderful parallaxes by Fritz Benedict that gave us better anchors in the Milky Way, have all stayed in the same ballpark as we've gone along, but the error bars have gotten smaller. And we have 2 independent groups making these measurements. WMAP and the cosmic microwave background have diverged, but the divergence has been there for a little while. But now the error bars are small enough that we believe it. And what's happening here, as we heard yesterday evening, is that the data is just getting better and better. And right now, if you take the 2.4% measure from Adam Rees and the 1.3% measurement from Planck and BAO, both measuring the young universe, there's a 3.4 sigma tension, which is a 96 percentile difference, and that's a big bummer. And we don't know what's going on. So what could be causing this? There could be systematics that we don't know in either set of measurements. We could be missing physics in the standard cosmology. That is the most exciting thing to go for. Number 1 being the most likely, number 2 being the most exciting. We could be missing physics in the stars. It's incredibly likely, but we've been studying stars for a long time. Or there could be something even more wicked, because we don't know what we don't know, right? So to just pick something from this list and to run with it is not understanding the history of the Hubble constant, I think. Another thing to mention is that there have been reanalyses. So most of these H0 measurements from the distance scale are coming from one or two teams. Independent analyses are really important. There's many of them in the literature. This one's my favorite by Bonnie Zhang because they note that during their reanalysis of the Rees et al. 2011 result, we obscure the value of H0 throughout our analysis in the first stage of the referee process because calibration of the supernova 1A requires a series of often subtle choices and the potential for results to be affected by human bias. Okay. So she kept it blind. She had no idea what her H0 was. They actually find a value that's not so different from what Rees et al. Found. But the error bars go from 3% from the 2011 measurement to 4%. So they get a fairly big uncertainty difference. And then here's the part. Our error budget is dominated by statistical errors due to the small size of the supernova sample, whilst the systematic contribution is dominated by Cepheid period luminosity relationship, the supernova 1A systematics, and uncertainties in the host galaxy mass dependence and the Malmquist bias. These are all our friends if you're in galaxy land or star land. We know that these are problems that we need to understand, and she says it quite elegantly in this paper. So the question that you're probably wondering is why are there so few calibrators? And if you go through the literature, you'll get many postulations about why this might be the case. But the first thing that pops into a lot of people's heads is, well, supernova 1A are rare. Sure. They're rare in an individual galaxy, but there's a lot of galaxies. So here's a map here's a plot as of about the time of the Rees paper and my paper of all of the supernovae using their NED mean distance, which isn't a very precise way to do it, but it's a fair way to do it. So this is the number of supernova as a function of distance. So there's many dozens of supernovae within 40 megaparsecs. There's about 100. And then as you go out to 80 megaparsecs, it doubles. Okay, so there's many supernovae. There's many more than 8. There's many more than 20. So the next thing that you might think, okay, well, maybe all of these supernovae have been discovered fairly recently with all of these beautiful all-sky surveys that have come online recently. And that's actually not true either. If you plot the number of supernovae and their discovery year, you can see that we have had many more discoveries since the 2000s, which is when people got really excited about this, but that the last couple of years have been a very dry year for supernovae. We've actually had 3 nearby supernova 1A this year, and we had 1 last year and 2 the year before. So if you actually look at the number of supernovae within 40 megaparsecs is 95, and most of these were discovered a while ago. And I set this date, this is roughly the date where everyone agreed to use CCDs. So we tend not to use photographic plate measurements anymore on the distance scale. Okay. The other thing to keep in mind, so this is the Rees 19 supernova galaxies from 2016. These are the 0-point calibrators. And something to keep in mind to set you up for where I'm going is that you can look at this plot and you can see that not all galaxies are equally abundant in Cepheids. So, this galaxy has a lot, whereas this galaxy is struggling a little bit. And the thing to keep in mind is that different galaxies have different stellar populations. They have different morphologies as well. They also have different star formation histories. So this guy is having a starburst. It also means it's very dusty. Different problem. This guy's face-on has many, many Cepheids that are well measured. This is the one that's kind of struggling, and you can kind of see why. And then this is a barred galaxy where most of the Cepheids are out here in this ring. Okay? So not all galaxies are equally abundant in Cepheids. This leads into the reason why we have so few calibrators, and that has to do with whether or not a supernova 1A is suitable to be a calibrator. And there's 2 components to this. Can I characterize the supernova, and can I measure its distance? Okay. So the answer is, in terms of characterizing the supernova, because the supernova community said, hey, we have to get this right, you can actually do this most of the time. Supernova goes off nearby, the team is going to follow it, and they're going to follow it until they get the most beautiful data that you've ever seen, and I'll show you some. But the main concerns are, did I find it before peak light? Can I remove the galaxy or nearby bright sources to get a good measurement of that supernova? Do I have quality multiband light curves? I need to follow them for about 30 days to get that stretch factor right to use them as standard candles. And can I estimate local extinction and some related issues that go in there? So to demonstrate to you that this is easy, I'm going to show you the brief period of time this spring when I was a supernova hunter. So on the 10th of March at 4 a.m. UT, a transient was detected in this beautiful galaxy face-on spiral called NGC 5643. There it is, right there. Within 16 hours, someone had put a telescope on it, gotten a spectrum, and typed it as a young supernova 1A. It's not a beautiful spectrum, but it's all you need because these broad, weird emission lines are just dead ringer for being a supernova. So 16 hours is the delay there between discovery and being typed. And that's mostly where it's dark on the planet is what sets that delay time. And within 30 minutes, we were on sky with this supernovae, getting multiple phase points per night within 30 minutes of the typing, and we started building the light curve for this galaxy in 6 photometric bands. And I show here this galaxy actually had an earlier supernova that is not in the calibration sample from 2013, which has this beautiful data from the Carnegie Supernova Project in 10 photometric bands. But that has not been in the calibration sample because this galaxy is actually just out of the plane of our own galaxy, and it's usually not used for that kind of work. But if you work in the near infrared, you can use this galaxy. But you can see the difference that has come along because of fast transient detection, fast typing, and fast getting on sky is that we're now tracing these guys from delta minus 20 days instead of delta minus 1 day from maximum. And we're also getting data so beautiful that we no longer need templates. And I actually put my colleague out of a job potentially when we were able to follow this up. He got very sad and very excited at the same time. And it's also, I have to throw this out here, but small telescopes are very relevant. This is the 16-inch telescope and a 20-inch telescope that made those light curves. That's all you need to trace, to hunt supernovae. It's really stressful though, so I don't recommend it. And so thanks to a phenomenal effort from the supernova and the transient community, 40 supernova within this 40 megaparsec volume have enough data to be used as of 2016. So we've got another 5 or so since then, and that's about 50%. So we're still looking at a very large number of supernovae that are not in our calibration sample. So now the question, can I measure its distance with Cepheids? And the first questions I have to ask, is the host galaxy star forming? It needs to be relatively luminous, and it needs to be approximately face-on. And I showed you that in that little display of how those different galaxies were having different Cepheid populations. These are the limits that you have to apply on your supernova, your rare supernova. And if yes to all of the above, to measure a supernova Cepheid distance, I need 10 to 20 epochs of optical imaging to find the Cepheids and determine their periods. Then usually we go back in the infrared to use a tighter period luminosity relationship. Do my Cepheids span a range of log p? So you need a nice range of log p to make sure that you're getting that fit, and that is a function of the mass distribution of your Cepheids or the star formation history. Is there a spatially resolved metallicity information? There's a known correlation between a Cepheid's metallicity and its absolute magnitude. Very complicated, I can tell you about it offline. But basically you need to have some spatial resolved metallicity information for a galaxy, and then we can even argue about whether that's even appropriate to look at H2 regions in stars. And that's a whole other discussion. There are whole conferences devoted to that. Can I measure the local extinction to the star itself? Crowding. To put things in perspective, trying to look for Cepheids in the M31 from the ground is equivalent to looking for Cepheids with HST at M101 distance. And M101 is the closest supernova host. Okay, so think about trying to search for, think about Hubble searching for Cepheids and compare that to M101. And then a number of other subtle issues that we don't need to talk about. And this lies, and here's where you have a significant limitation. You can do all of this, but it's incredibly expensive. And it's up to the community to decide if they want to continue to put HST orbits into this thing. So to go after 10 supernova, for instance, you need something like 100, or 10 supernova with Cepheids, you need something like 150 or 200 HST orbits. So it's pretty expensive. So Cepheids are amazing tools. I love them. I study them. I spend so much time thinking about them. But for this problem, maybe they're not the best tool. So they got us from discovering the expanding universe down to a few percent. But maybe we should think about something else. Because the data is expensive, relies on numerous techniques, each of which have their own conferences devoted to them. And each of those things is an error term. And you have to know those error terms much better than you know anything else. And we could argue about that, how well we know that. So to go to the next part of the talk, which is what I'm doing about this, the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. Okay. And the eyes are the eyes of Gaia. Gaia is this wonderful trigonometric parallax mission. It's very complicated, but it's wonderful. And basically, you can look here at this tiny circle. This is the 10% parallax limit for Hipparchus, which is 100 parsecs. Tiny. Gaia will get you 10% distances at 10 kiloparsecs, or 10,000 parsecs, which is this circle here. And that changes things. So I do have to mention that HST fine guidance sensor does give us parallaxes to larger distances and higher accuracy often, and precision. And a great example is for RR Lyrae. And those measurements are much better than even, I don't know, than Gaia DR1, DR2 potentially. So what Gaia does is it's going to give us the entire color magnitude diagram, the entire HR diagram with parallaxes. Okay, so this is a preliminary DR1 HR diagram. So if you don't look at CMDs all day like I do, this is the color axis, which is probing temperature, hot stars, cool stars. And this is the luminosity axis, which is going in the opposite direction, et cetera. So brighter stars, fainter stars. And this is using J minus K colors and then an absolute V-band magnitude. So if I'm thinking about supernova 1A hosts in mass, and I'm thinking about orbit allocations with HST, I pretty much need to like blow out everything sort of on the main sequence. It's just too faint. For reference, this is where the classical instability strip is. So your Cepheids are sort of up here, or yeah, in here. And this strip just goes across. And I'm going to label a couple of different techniques, and I'm trying to put them roughly where their magnitudes are. You can actually see in this Gaia DR1 how the luminosity bias, because we're in a small area. So I don't have these very luminous things are underrepresented, as you expect. So some of these techniques are along the horizontal branch. You can use the red clump or the RR Lyrae. But they're about an MV of 0, and they're pretty faint. And that's actually unrealistic, even with JWST, to go beyond a few megaparsecs. You can also use the Cepheids, but we just talked about them. You can use Miras. So Miras are an intermediate age population. They have long, long periods, and they're complicated. They're AGB stars. AGB stars are complicated. We'll just leave it at that. So Miras are tantalizing, but we're probably not there in mass. And the other option is this tip of the red giant branch. And that's what I'm going to tell you about. So the tip of the red giant branch is literally an assignment that all of you, the physics, you've all done in your undergraduate physics class. So here are fiducial sequences, and the step here is in metallicity. Basically, as a star goes up the red giant branch, its helium core is degenerate, or its core is degenerate, and it has pressure from the outer parts of the star. It reaches a certain temperature in that core, it breaks the degeneracy, and it moves on with its life. And that cessation is very quick, and because it's a core temperature, because it's hitting the same temperature in the core, the bolometric luminosity is fixed. And I guarantee this is in your stat physics book, this calculation. So what happens is that bolometric luminosity is attenuated differently in the atmosphere of the star depending on the metallicity. So in the optical bands, where you have line blanketing in the blue, more metal-rich stars look fainter than metal-poor stars. In the red, in the H band, that that energy that was absorbed is re-emitted thermally, and you get a tilt in the opposite direction. Somewhere around the I band, those effects sort of balance each other out, and the tip is flat. So to use this as a distance indicator, I have to detect this tip. And an advantage of old stars, like RGB stars, is that I can measure distances to galaxies of any Hubble type, any inclination, any luminosity, any property you can give me. I can measure a distance to that galaxy if you give me enough HST orbits. And that's really important. And we're also going to use the halos of galaxies way out there, actually more like out here for Andromeda, to do this measurement. And we've gotten rid of crowding because it's low density. We've gotten rid of extinction because there's no gas in the halo. Really, there's not much. And we're using old stars, so we're actually looking at the same stars that formed 10-ish gigayears ago in all these galaxies. We're not worried about something weird happening in the evolution of the galaxy that made the Cepheids different, which is something we worry about. And they're almost always metal poor. So the pros, not variable, well understood physics, applied to all Hubble types, all inclinations, all luminosity classes, down to ultrafaints. You can't do this in ultrafaints. You can apply to low density regions of galaxies, few differences between local stars and distant stars. The metallicity effects are actually projected into color, which is super useful because color I can give you, I can measure. Metallicity, maybe not. And I need a single data set to find and characterize. And it's red. These stars are red, which means in the IR revolution to come, we're well suited to use that. The cons are we don't have a century legacy. The literature, we have to solve a lot of problems with how we're using this, and there's no direct trigonometric calibration, but now I'm going to show you that we can handle all of this. So this is our sample that we have to build. We have to measure our distances for the first time to all these supernova hosts. We have to do all sorts of tests in the local group, these are dwarf galaxies, to prove our precision, and then eventually we have to measure parallaxes. But we're doing it. It's all in my paper. 2, we have to do standardized techniques. And so to show you that we've got this, I'm going to show work in the near field for IC 1613, which is a nearby dwarf galaxy. Here it is. It's see-through. It's one of the coolest galaxies in the world, or the universe, sorry. And then I'm going to show you a far-field galaxy, which is NGC 1365, which is just this brilliant borrowed spiral in the Fornax galaxy cluster. And this was work that was led by Dylan Hatt, my student, who just got his PhD this spring. So now I have to call him Dr. Dylan, and then In-Sung Jang, who was a PhD student when he started working on this project, but now is in Germany. So to give you a sense of what we're looking at, here's our ACS field. We're off this galaxy. There's no dust there, and to convince you that there's no crowding, we're going to zoom in. Here's our actual ACS field. Zoom into this tiny little region, and these are our RGB stars. They don't know about their friend RGB stars. Halos are wonderful. Here's the equivalent. We have to do this from the ground, actually, and then we map it up to HST, because nearby galaxies, this is the ACS field, and we just don't have the statistics. So what does it look like? This is IC 1613. There's the tip right there. It's beautiful. This is a distant galaxy Fornax data cluster. The tip's in there, and you can see it. So the difference in signal to noise here is quite considerable. These are 0.01 magnitude uncertainties on these magnitudes. These are more like 0.05, 0.06. But that's what happens when you're working in the Fornax cluster. So how do we measure the tip? Well, we basically do a color selection to get rid of young and intermediate age stars. We collapse the color axis and build a luminosity function here. Here, you don't have to do anything. It's right, there's the tip, it's right there. But then we basically do an approximation to the first derivative to look for the place of greatest change. And that gives us the tip. Here's a distant galaxy. We do the same thing. Collapse the color axis, run that filter, and get it there. Noisier, we know that. It's further away, but still pretty good. So we get a distance here to about 1.5% statistical. The systematic precision has to do with our absolute calibration that we're still working on. And here we actually get a 2% distance to NGC 1365. Equal precision, near and far. Awesome. Just really awesome. So this, we just resubmitted this, a reply to the referee, and this one's been accepted. How do we get our uncertainties? This is a complicated figure that I won't go through, but it's here if you want to look at it. But basically, we simulate it. We do an idealized RGB based on all of our knowledge of the RGB, drop it into our individual frames, throw it through our photometry, through our analysis technique, subsample it, make all sorts of measurements, and we get our systematic and our random uncertainties direct from the data, and making very few assumptions, except that we have a basic idea of what the luminosity function looks like, which is a pretty good assumption. So you can see here, IC1613 high signal to noise. You see no difference between the output, which is in yellow, and the input, which is in black. For 1613, much further away, you can see how those photometric errors blur that tip. But like I said, we can study it and understand it. We use some specialized techniques that we've developed that we think are pretty immune to some of the common problems. But in the appendices that are often longer than our actual papers, we demonstrate that our methods are consistent with everything that's been done in the literature to our best understanding of their uncertainties, which sometimes requires deriving all the uncertainties ourselves. But it all is consistent or understandable. So 2% distances to 20 megaparsecs, pretty awesome. To demonstrate that I didn't just pick my favorites, this is M31, equivalent measurement for M31. There she is. And 1316, which is the central galaxy of the Fornax cluster. There it is. Awesome. Also in standardized techniques, you might think, so with Cepheids, you're stuck with the Cepheids you have, or you're proposing to find more Cepheids. With a TRGB, we can just look at another field. So this is M101, which has tons of archival data. And what I've done is I've actually measured the tip in all of these fields. These two are hopelessly crowded. Hopelessly. The Cepheids are found sort of all over. But here's field B. This is the one that's our optimized detection here. There's the tip. And then you can see it in these other fields which aren't optimized to do the TRGB. But if you're smart and know how to use it, you can find the tip in these fields as well, and we can test how well we're doing. It turns out the way we pick our fields is to use our knowledge of galaxies, in that we can make surface brightness profiles. And surface brightness profiles in the WISE band trace old stellar populations, and the near UV and the FUV trace the spiral arms and the star formation. So we can make sure we miss faint spiral arms and we don't land on an area of confusion. And we demonstrate that clearly with M101. Awesome. Direct calibration. We're going to have Gaia, and it's coming, but Gaia doesn't do it all. Gaia is going to give me a parallax, not a distance. It's not giving me an absolute luminosity, just a parallax. So to actually make this measurement, we're using these tiny telescopes to actually go collect all the photometry that we need to do this properly. So this is our TMMT, stands for the 300 millimeter telescope, which is cheeky, and I like it. So this is our initial campaign, and these are their Hipparchus parallaxes. These are real error bars. And we thought, oh, look, maybe this is the tip in here. Here are the T-gas parallaxes, and the blob, which I like to call this the blob, has turned into a beautiful red giant branch sequence, although the error bars are still too big for us to not believe that we're fooling ourselves. So be careful with noisy parallaxes. It's really important that you use very good parallaxes. We also need parallax-independent ways to define our samples so that we're not biased. So we would like to use stellar parameters from Apogee and TESS. And so there's my Apogee connection. That's all I'm going to say about that. We're also building a near-infrared version of this telescope. I just got the funding like 3 weeks ago. So we're going to have a near-infrared tiny telescope doing magnitudes and light curves, hopefully within the year. But in the meantime, we're using RR Lyrae. RR Lyrae and the near-infrared are very precise. Probably don't have time to tell you this, but it's really cool. So this is UBV, R, I, J, H, K, L, and M bands for RR Lyrae. And this sawtooth shape that you have in the optical turns out to be mostly due to the temperature effects of the pulsation. As soon as you get into the H band, all you're seeing are radial effects because you're off on the Rayleigh Jean's tail. And you can just do exquisite distances with RR Lyrae and the near-infrared. The period luminosity relationship, the scatter for an individual star, if you know the metallicity, is about 1% for an individual star. If you don't know the metallicity, it's more like 3%. for an individual star. And then we're working on calibrating this with Gaia as it comes out. I literally have the code ready to run, but right now the errors are just too big. So the TRGB, my cons were no 100-year legacy. We're working on it. Great non-uniformity. We've developed and demonstrated the techniques that we can use over 10 magnitudes in distance modulus. No direct trigonometric, no direct calibration. It's coming. Gaia's coming, and we're out there every day trying to get ready for it. The take home, however, is that we're not seeing large differences between using the TRGB and Cepheids right now, but we're not fully independent because of how we have to do our 0 points. So this is a simple diagram because there's literally only like 10 distances to 1365. For IC 1613 in the local group, there's many different techniques, many different teams, many different groups, which is why our local group work is so important to understand our biases and our true precisions and accuracies. So here are all these techniques, and you can see we're starting to come to a consensus on this dwarf. Now, in the last bit of time that I have, I'm going to talk about the future. And here's that tip of the red giant branch that I've been talking about in the optical. And so here's B, V, R, I, J, H, K, L, and M. And then here's a sense for where our favorite space telescopes are working. Although WFIRST, I think, is going to have something over here maybe, but I think that meeting, we'll see how that goes. So here we're looking in the blue, and here are our Cepheids. We can see clearly why we weren't using tip of the red giant branch in 1929. Here we go. But as we go to the J, H, and K, the tip is now as bright, if not brighter, than the shortest period Cepheids that you use in the distance scale. And all I need is one color magnitude diagram. I don't need light curves. So it's an order of magnitude more efficient. In the L and the M, the trend sort of continues, but the tilt of the tilt gets kind of funny, but the photometry here isn't great. So the jury's still out on that one. Future missions are in the near infrared, but what we have to do is figure out how to do our detections with this tilted tip. So right now we're calibrating the slope, rectifying it out and running those same techniques and getting beautiful high precision distances. And the test, because this is always the test, by a wonderful student you might recognize, Taylor Hoyt, who's at the University of Chicago, is the LMC. And Taylor says, don't overinterpret the maps. I don't trust my error bars. Okay. So this is a beautiful image by Gertina Besla and company of the LMC. This is the true extended structure of the LMC. This is the 2-mass photometry. So there's the main part, and then you can see all this extended structure. And what Taylor does is he divides these maps into different regions where we have equal numbers of stars. And the color here is the IR TRGB distance from 2-mass. This isn't even great data. And what you can see is we have one distance. There's the bar there, which is this sort of far distance because it's tilted. Then we have the disk, which is the extended disk, which is sort of face on, and you see we get relatively consistent distances. Somewhere over here is a ridge of gas, and we get more distant things because there's more gas there, more dust. And then we get this extended part where we also see some sort of twisting going on, and then far and near there. So not only is this technique exciting to do the distant universe, we can actually resolve the substructure of our friend, the LMC. This is pretty powerful. And so in conclusion, what we're trying to do is we're trying to get to 1%. We have to shorten the ladder so that there are fewer error terms, but we also have to open up the ladder so we can access every supernova possible. And to conclude, I love to use this quote by Alan Sandage that appeared in his obituary. He says, "It's got to be fun. I don't think anyone should tell you that he's slogged his way through 25 years on a problem and there's only one reward at the end, and that's the value of the Hubble constant. That's a bunch of hooey. The reward is learning all the wonderful properties of the things that don't work. So is my way going to get us to 1%? I don't know, but I'm having a great time doing it. So thank you."
Gerard DeVoe-Valor, who was on the faculty here, spent much of his career on the quest of the Hubble constant. Only his distance ladder was a picture of the Eiffel Tower. Remember that?
I think so.
Being French, you can't.
And it's very lattice work, which I think is
Yeah,
more...
right. Put a wide base, right?
Yeah. And you need a wide base.
Yeah, you do.
Yeah.
Okay. Earlier in the beginning, you mentioned this 3.4 sigma difference in H-naught, and then you said a PTE of 96%.
Yeah.
Is that because you've taken into account some non-Gaussian shape of?
No, that's just a simple way to think about it to emphasize what that actually means.
But I mean,
Yeah.
3 sigma is like 99.5%, right? So 3.4.
Oh, yeah. So I did the conversion wrong. Yeah,
Okay.
that's pretty typical for plane. Yeah, no, it's serious though, right?
Yeah.
Yeah. Maybe I assumed a different confidence interval or something. I don't remember. But yeah, it's troubling, but probably systematics for us at least.
Other questions? I will use my prerogative as chair. There was like one line in there that you mentioned you're getting properties from tests. Is that like astroseismic or?
Yeah, so there's two things that TESS is useful for. One, we don't actually know how stable these magnitudes are. So TESS is going to stare at these guys in the continuous viewing zone half a year, and that will actually give us some pretty good information about whether these are stable or not. And we need to kick out things that are varying, and it turns out a lot of things around the tip are varying for various reasons, and I don't actually know if they're tip stars or if there's something else that happens to be there. So TESS will give me that, and I'm really excited about that. We're looking into Flickr, which will give you a log G, which gives you an independent way for many, many stars to get rid of things that are not true tip stars. So that's what we're working with now, and our hope, so Johanna, who will speak in a moment, we are trying to follow up the entire TESS continuous viewing zone in the north and the south with Apogee, which will give us an incredible database. So if you don't know, Apogee is a stellar spectrograph in the H band. You get 15 stellar abundances, and you get stellar parameters. And for me, on the red giant stars, Apogee is perfect. Right, Sten? Yeah, Apogee is perfect. So we get all of this information about the stars to calibrate metallicity effects. And when you combine with Gaia, you can get ages. You can test for age effects. But it also gives me these stellar parameters to say, oh, that's a heavily reddened BE star, which happens, and things like that, that I can only get through spectroscopy. There's also a way using Apogee spectra to get direct line-of-sight extinctions using diffuse interstellar bands, which is pretty good. I mean, it's better than most ways. And we'll have like 8-band photometry for all of our tip candidates, at least in the south. So we should be able to solve a lot of problems with this data set, but it requires a global effort sort of to get all this together. Absolute luminosity calibration is hard. It's just really hard. Yeah.
I just have one more question. All right. If not, then